So first speaker today is Michael Walter from Amsterdam, and he's going to tell us something about home circuits for the Dirac field and 1+1 matrix.
Thanks very much, Sophie. Thanks a lot to all the organizers here for having me speak. So last time at the DESY was really great. I'm sorry for missing the first 2 days of this workshop. I had to teach. So I'm sure there were lots of great talks. The one I saw were really interesting. So today I want to talk to you about some drawing work with various people. And so I guess yesterday a trend was that to announce preprints in order to put pressure on our collaborators. So I did the same. I was less courageous. I didn't put a 0 here like Bartek did. But at any rate, so what I want to talk about is a tensor network construction for a very simple theory, but it's sort of a complicated construction. And the reason why things are a bit complicated is because we want to get rigorous guarantees about how well we approximate correlation functions in the actual continuum theory. And so that's joint work with Sveik, who's sitting here, and it looks like this. So you can talk to him also in the breaks, as well as with Volker Scholz and Brian Swink and Merrill. And it's sort of partly building on older work, also with Yuto, Jordan Kotler, and Glenn of course, there's well-known on having worked on Camera tensor networks, and we will also talk about Camera tensor networks. So I'm in Amsterdam, and I guess the reason why I say quantum circuit is because I work at QSoft, and we are a center for doing quantum software, which means we do research on quantum information and quantum computing, but also the tensor networks that we are going to use are unitary transformations, so they have the interpretation of the quantum circuit. That will be interesting for some applications. That's sort of fuzziness when I change slides. I guess we can meditate for 2 seconds before we focus on the content. So I guess the first part of the slide is of course unnecessary. So we all know and love tensor networks, for example, because they provide us with efficient kinds of variational classes for many-body quantum states. So we have a tensor with many indices, which is a wave function, many-body wave function. And we can then represent this as a contractor of smaller tensors. And I guess, at least the past 2 days I was here, we mostly saw matrix product state and PEPS tensor networks. There's other kind of tensor networks where you, for example, the one called NERA that we'll zoom into in a little bit, where you're describing a one-dimensional system, but by a two-dimensional tensor network. So there's some notion of a bulk, and there's some meaning to this bulk, and we'll talk about this in a bit. Now, I already mentioned this, so we're joking in the last slide, some of these networks have an interpretation as a quantum circuit that can be interesting when the bond dimensions become so large that you cannot no longer efficiently contract things on a custom computer, and you may still be able to compute observables or correlation functions on a quantum computer, so that may be interesting. It's also interesting because it will unitarily map degrees of freedom, for example, one-dimensional degrees of freedom into a two-dimensional fashion, so resolving things into scales, so that's something we'll come back to. So these are tensor networks that whatever, in some sense, whatever network structure you choose, you get a variational class. Now, I guess we like these things because they're useful for numerics, but then we also like them for theoretical reasons. For example, one thing they certainly do is they, in some sense, geometrize the entanglement structure. So they give us a cartoon of the entanglement structure for many-body state. This was all already explained in Ignacio's talk, the first talk I saw after arriving. And so the reason is basically whatever network is choose, you get sort of a generalized kind of area law. Basically, you just have to cut the minimal number of bonds separating the subsystem you care about from the complement. This gives you a bound, and that was of course also inspired some connections to holography, because this is in some sense a minimized area law. It looks like the Vito-Tokanagi formula. In general, of course, it's only bound. Another part of this dictionary of the formalism that's useful is that we can often get what you could call bulk boundary dualities, or dualities, this may be a strong word, but sort of mappings between degrees of freedom and physical sites, and on these virtual sites that we would name by cutting open your tensor network. So that has been very useful to study all sorts of things, to sort of, for example, to study topological order, symmetries. Also, Ignacio mentioned this. You can sort of, if you have a global symmetry in your state, you can sort of implement this by acting on the virtual legs, and in some sense, even only if in one dimension, in higher dimension, we can at least use it to produce symmetric states. Some of these networks have an RG interpretation. We'll come back to this. And again, of course, some motivations by making contact with logos. So this is the kind of network we want to focus on. I want to draw this in different ways. It's called a NERA, or it's a version of mirror, which is short for multi-scale tangled realization ansatz, put forward by Giffre Vidal. And I want to discuss three interpretations of this network. So this is maybe a weird rendering of a mirror, so we'll sort of unweirdify it as we move along. So the first way I wrote it is the way that makes it clear that this is a quantum circuit, which means that we start with a simple state, say a product state, and then we act by gates, so local operators. And I mean, this looks quite non-local, but you see that almost all the lines are going over the box. There's only two lines entering and leaving the box, and these are two local unitaries. And so we are preparing some complicated many-body states in a fashion that is basically similar layers of float-F quantum circuits. Okay. Now, the picture will become more familiar. I push down these input states as far as I can, so adding ancillary systems whenever needed. And now it's very clear that these layers are indeed self-similar, and sort of in each layer, I suppose, well, if we start at the top, we add detailed degrees of freedom. If we start at the bottom, then we are coarse graining. So this is where this name entanglement generalization comes from. And the self-similar nature is also why some of this ansatz has been put forward to describe critical systems fundamentals, because it's in some sense scale invariant by design. And there's a pleasant interpretation sort of what's going on here, and which is namely that the cartoon we have in mind is that each of these layers is trying to disentangle local degrees of freedom. So if you have some local bit of entanglement, you could, using this network of unitaries, or using a more conventional rendering that emphasizes, sort of what's called a disentanglement, so the isometry, off the isometry, you can sort of disentangle local degrees of freedom, say using this network here, and then we project out the modes that would then correspond to these local entangled modes. Okay, or the other way around, sort of if you just take it from here, you take a sort of each of these legs, you insert some state, and it produces some, so by the light cone nature of this network, some local node down here. Okay. And I guess then there's motivations for how you can actually arrive at this network structure by TNR, which TNR we saw in a previous talk, by sort of taking Euclidean path-like description of your quantum state and then trying to coarse grain the tensors as much as you can do. So this has also been illustrated in some examples. I think about Ising theory. All right. Then the last thing, of course, is that so here I have the perspective that I'm preparing a single many-body state at the bottom, but I could also just remove these input states over here, and in this way have a unitary transformation between this one-dimensional system at the bottom and a two-dimensional Hilbert space sitting at the top. But two-dimensional, I mean just that the subsystems are labeled by not only by x, but the position, but also by scale parameter. So so this looks like this. So these dots just indicate, I mean, they're just dangling edges, and there's no particular reason I write it as a dog, except to emphasize it. So I no longer put in a fixed state, but I just have a transformation from a one-dimensional system to a two-dimensional system. So n degrees of freedom get mapped to n over 2, n over 4, n over 8, or in the continuum, this sort of density of systems sitting here. And so intuitively, you could think about this transformation as somehow, well, we would like this to somehow organize our quantum state, our quantum information sitting at the bottom, and the one-dimensional system in some sense by scale. Okay, and we'll make this more precise as we move along. When I move from this description of a quantum state to this description, there's some ambiguity, because really somehow these maps here, these gates, they were only defined, the action was only defined when I inserted zero state. So in general, there's infinitely many ways of extending this, and there's no a priori physical meaning to this two-body operation itself. But in some cases, we can actually construct these tensor network descriptions in a way where we actually construct the whole unitary transformation, this holographic mapping, if you wish, in quotes, such that when we insert a particular product state, say the all zero state, we get the ground state, but if we insert another state, we get some kind of excited states. And that's also what we'll see for the simple Dirac fermion theory that I want to talk about. All right. So that's so in some sense this really well, it makes this a more meaningful mapping, right? Because you start with a mapping, then you recover states as a consequence. Another sort of connection here then is, I mean, once you have a mapping, you can go wild, and Brian a while ago observed the similarity of this sort of hyperbolic structure of this network with a time slice of ADS, and you can sort of draw a similar version of this network, you can also draw on say, this over here. And it's not exactly the same network in part because it's not very deep. But if you imagine this go out all the way, then locally this will look like exactly like this network over here. And so he proposed that maybe there's some actual connection between ADCFT, between the holographic, between ADCFT and these Mara tensor networks. And there has been a long discussion about where does this network live. Many people have opinions. I don't, so I don't want to talk about it. But in part because okay, let's not go into this because in part because I'm not describing holographic theory, so I don't have to commit to any particular interpretation. But it certainly it is true that this idea of using tensor networks to not only describe states but to define linear maps between two systems of different dimensionality has then given rise to a lot of interesting research. Sort of on the ADCFT side, and also to some toy models, such as the one put forward by John Prescott and friends, and using these perfect tensors, which I think popped up on Monday or Tuesday, and these random tensor network models that we did with Patrick and friends a while ago, where we're kind of building these holographic mappings in such a way that they imitate properties of ADCFT. And at the last installment of this workshop, I spoke about this line of work, so I did not today. One interesting feature, which has been proposed in the ADCFT world, is a kind of an error correction property. That sort of, I guess Bartek has mentioned entanglement wedges, and I suppose you spoke about how information in an entanglement wedge we believe is dual to the reduced density matrix. So in some sense, this logic, if one turns it around, it kind of tells you that somehow degrees of freedom that are somewhat deep on the bulk or further up in the network, they're sort of protected against erasing part of the quantum information here. So one can make this precise. It's called an erasure code. This sort of quantum error correction property is in some sense very general. This has been understood by Isaac and friends. And it's basically saying whenever somehow the only operator with scaling dimension 0 is the identity map, then you always have this kind of error correction property because things here get rescaled as you move them through the network. And one can make this precise. One can look at what's called the scaling superoperator, look at its eigenvalues, and if there's a spectral gap, then there's always this quantum error correction property, which at the same time has a very useful sort of in practice meaning, which is that it makes this whole ansatz noise resilient. So by this I mean the following. Suppose you want to do some variational optimization using this ansatz on a quantum computer. Now the quantum computer is pretty bad because it's 2019, and so you cannot do these gates exactly the way you want. So make a little error, and you might imagine that the errors accumulate sort of additively as you move up in the network, or maybe even worse. Now, what some of our followers from this kind of this renormalization kind of bit by the spectral gap is that in some sense it's not the case. Even if you make the network deeper, some errors accumulate less than they could by a naive accounting. And this is something that Ryan and Isaac pointed out, and they put forward actually using Mara as a variational ansatz on some hybrid schema. You have a quantum computer that you use to estimate, say, expectation values, and a classical optimization routine on top, and some sort of feed-forward cycle, motivated by these ideas. So it's kind of interesting, I think, that this sort of very abstract error correction property that we study in holography actually is also reflected by a very practical property, that may mean that this is a useful thing to do on near-term devices. Okay, so that's my sort of Mara introduction, and so now let's move towards quantum field theories. Now this is of course not something we have to discuss in this workshop, but I guess if you want to model a quantum field theory on the tensor networks, then a priori there's some problem, right? Because our tensor networks are usually finite representations, maybe discrete in the standard renderings that I drew. While quantum field theories are often, they usually have infinite many degrees of freedom, and we like to study them in the continuum. And so somehow there's two approaches that one can take, right? One is sort of, well, we embrace the continuum, we change our ansatz. For example, we look at CMPS, the continuous matrix part space, C-Mara, and so on and so forth. Or we stick with the lattice. So in the first case, well, in principle now we have we define a many-body state on a continuum, but of course the parameters, the variational parameters are also become continuous. Okay, so that's maybe a downside in some sense, or maybe not. On the other hand, we could stick with a finite representation, so what I call lattice, or maybe I should have written discrete here. But then it's less clear what the connection is between what the network describes and what the actual theory contains. Okay, so there will be some in either case, you will represent part of what you want to represent, but it's sort of the intuition is a bit different, or the way of thinking about it is maybe a bit different. And I guess one could further distinguish the second part into one case where you actually change the theory you're looking at. Maybe you put your Q of t on a lattice, and then you're trying to approximate it. Or you could say, I have a discrete network, but I still want to make statements about the continuum theory. And so this sort of third point of view is the one you want to pursue here. But whatever you choose, I guess there's a bunch of questions that arise. So one is because, in the end, you will have a finitary representation. What aspects of your theory are being captured by the tensor networks? And of course, there's answers to all these questions. I mean, depending on who you ask and in which approach you ask these. So the second question is, how do we actually measure goodness of approximation? Because something that we cannot do, we cannot simply look at something like the difference in Hilbert space, right? The norm difference between one many-body state prepared by the tensor network and the actual quantum field theory state. They live in different Hilbert spaces. Somehow the norm difference will always be one. And so this is not a meaningful thing to do. So we should focus on some more operational principles. And of course, what you should focus on is correlation functions. And then this is the next slide. Now, once we fix sort of a measure of goodness of approximation that we care about, we can ask whether there's any rigorous construction principles by which we could actually construct a tensor network a priori, or maybe algorithms that have a rigorous guarantee. Now, of course, these things are more subtle because it's hard to define QFTs in general in a completely rigorous and satisfying way. It's something that is well understood, well, say, in a lattice system, and there we know all these things. So, for example, we know from work of my tastings that if we have a gapped system on a one-dimensional lattice, we know rigorously that we can approximate ground states up to precision epsilon by a tensor network of a matrix product state that has one dimension, polynomial in the system size, and I think maybe poly log 1 over epsilon or something like that. So so what this is saying is that matrix product states provably are a good answer for one-dimensional gapped lattice systems. Okay, so we don't know such a thing in 2D, but of course there's lots of evidence that things work well, as we also saw this week. And then this is sort of an existence result, kind of based on establishing an area law, for example, or some kind of decay of correlations in another approach. But then you could ask, can I actually find this matrix product state? And again, I guess there's two camps, right? There's one is sort of do an algorithm that in practice we know works, and the other is sort of try to come up with an algorithm that provably works. And so in the quantum information community, people have also tried to, for example, they have tried to make DMRG rigorous. So they found different algorithms that now are close and close on spirit, but where they can actually prove that they work. And so in some sense, the ambition would be to pursue a similar program, but now for more complicated theories. Complex theories. So this is then what we want to do. So somehow, the perspective I want to have, and I guess I'll not be super precise and detailed about it, is that if I have a continuum theory, I would like to make statements about the continuum theory. I don't want to put in on lattice, but at the same time, I want to use a discrete tensor network. And so what I'm going to do is, my ambition is going to be to approximate correlation functions of the continuum theory, which I write in a cartoon way like this, but of course there's no density operator, no trace a priori, and QFT. So I'm fixing some set of operators that I care about, and then I'm going to look at expectation models of not too many products of those. And then I would like to say that such a correlation function in my continuum theory is well approximated by some other correlation function I compute using, for example, a mirror tensor network. Okay, so that's the kind of thing we want to do. And it's sort of so that's some of the third perspective I mentioned before, and sort of it sort of unifies kind of the continuous and discrete, because somehow it doesn't matter what the dimension of whether your system that you want to probe is continuous or discrete, because it's just discrete because you probe it in a discrete fashion, right? So because you're, for example, and so discrete I mean in a general sense. For example, you could have some lattice spacing in mind, but maybe what you should do in a quantum field theory is more like you should look at smeared field operators. That's also going to be what we are going to do. Okay. Suppose you did this approach in lattice, then it's of course, if you have a tensor network for the whole state, this is of course sufficient to give you a tensor network that computes all kinds of correlation functions. But it's maybe not the most optimal way. For example, suppose you only want to compute 2-point functions. Then in some sense, maybe you could do it with a Gaussian state or something, right? That has the right 2-point function, which is much simpler to prepare than the actual state you care about. So that's sort of, I mean, it's sort of a trivial point, but it's also a bit interesting, I think. Now, there have been a bunch of works that took this seriously, and so I want to particularly emphasize the work of Hilbert and Volker, where they really show that sort of in some sense a Hastings-like result for a subclass of rational CFTs, and where they show that one can compute, that one can construct matrix product state approximations that allow you to compute correlation functions in these in the vacuum state of these CFTs. And again, there's some epsilons and deltas floating around, and they are very precise about this. And so in some sense, what we're interested in is doing something similar, but for these mirror tensor networks, because we like this interpretation of the networks as implementing some kind of renormalization. So this sort of additional sort of physical structure we would like to see in the networks, and that makes the problem a bit more complicated. Yeah. So this is roughly then the kind of results I want to talk about. So one is, so the result is basically that we construct these mirror tensor networks for very simple theories. Namely the Dirac fermion, both in the continuum and the lattice. I'll briefly start with the lattice just to sort of set up the notation, then we'll talk about the continuum. And then there's sort of an offspring that's maybe less interesting today, but maybe I'll have time to mention it. There's also a two-dimensional version of our construction, and its main interest, I think, is because you recover something that is called a branching mirror. A branching mirror is a certain network structure for two-dimensional systems where the area law is violated. And we know that a mirror in 2 dimensions cannot achieve this, a branching mirror can, so this has been put forward. And here we see an example of a critical theory in 2D where actually we get this branching mirror by really a principled construction. It comes out extremely naturally from the single particle level. I think that's well, we weren't aware of such a connection before. This is from the older paper with also with Glenn and friends. And so these tensor networks, the kind of results we will get is that correlation functions are well approximated in a rigorous fashion, and that indeed these tensor networks have this interpretation as mirror tensor networks, or Hammond renormalization quantum circuits, or the branching version in the two-dimensional model. And just to say this again, so we don't do numerical optimization to find the tensors, but we sort of give a by-hand construction of the tensors. And so basically you tell me the precision you would like, and I will tell you the tensors. Well, on my computer will tell you the tensors. It's still somewhat complicated. It's large matrices. And so the key feature, which I think is of more general interest, is to use wavelet theory. And the paradigm is kind of that wavelets are the single particle version of a mirror transformation. Because what they achieve is they decompose a signal, say on a line, they resolve a signal kind of into wave packets, localized wave packets of different scale. And that's sort of the first quantized version in some sense of what these mirror networks are supposed. They are supposed to decompose a many body state into scale and location. Okay. And so that's why this is natural. So here's sort of a cartoon of the kind of results we're looking for or we're getting. So here, for example, this is the most simple prefermion you can imagine, just hopping fermions on a one-dimensional infinite lattice at half fitting. It's also true that this model is unitarily, up to local unitary equivalent to one-dimensional Dirac fermions if you put them on a lattice. So the discretized version of 1D Dirac fermions in the staggered formalism that was mentioned also on Wednesday. And of course, you can easily solve this in your sleep using Fourier transforms, but I don't allow you to do Fourier transforms because I want you to use a local quantum circuit. And that makes things a bit more complicated, right? Because some of the Fourier transform, of course, resolve things into scale, but not in a local fashion, right? Because these waves, they're supported everywhere. So that's sort of all the 10-second summary of why something needs to be done to get a mirror network. Okay. And so then what we are trying to do is to get the clicker to work. So what we're doing then is we're constructing these networks. They look like this. So it's the same scheme as before. There's some local quantum circuit. I drew a box around it. The same box is repeated here, but in a cross-grain fashion. This is this state I called 0 before this. And so it's not really important what the fine-grained structure is at this point. So we construct these networks, and what they achieve is they achieve computed correlation functions. So we have a bunch of periodic creation and annihilation operators. F are some single particle states on the lattice. So right, F1, F2, so you're creating those guys, annihilating those guys, compute the expectation value or something like this. And the kind of results that then here you get, and here because it's on the lattice, I don't have to tell you how to map these Fs, from between continuum and lattice or something like this. So these are just single particle states on this 1D lattice. The kind of results we get is that the exact correlation functions in the simple theory are approximately equal to the one calculated by our construction, and the point is that we understand this wiggly line. So we can make, on one hand side, once you fix what you want to calculate, you can make this arbitrarily small. And I will give you a more precise bound later just to give you the feeling. So for example, you would expect that if you add additional layers, the approximation should get better. But maybe that's not the only thing, because if your tensors are not good, then it doesn't help to add many layers. And so we'll see this more precisely coming out. And the other thing that you would expect is that it's harder to approximate correlation functions as these single particle states, smearing functions, if you wish, become more and more non-local, and as you add more and more of them. And so this is also the kind of features that you reproduce.
So Michael, here, just to understand this picture here, right?
Yes.
So the solid lines or the dashed lines, is it
This picture?
Yeah. Is it two copies of the quantum circuit?
Very good. Yeah, I mean, for now, let's ignore it, but we'll come back to this in a second. So for now, just think of these as all being two local gates. All the lines are solid lines, and there's, say, one qubit sitting everywhere, corresponding to a fermion sitting on a certain side.
There are these swaps, right? But I mean, there's no crosstalk between.
Yeah, so these are just lines that run. I mean, so they don't talk; they're just one over the other. Yeah, that's all. Yeah, and of course, because this is a fermion many-body state, this is really a fermionic tensor network. So when I have crossings, I should probably be careful. But that's not. So let's not worry about this. Let's just imagine we identify this many-body state with occupation numbers at each side, which is 0 or 1, and then this is preparing the state. This is yeah. And we'll sort of understand some of the fact that this looks like two copies of the same thing, which is somewhat coupled here. We'll understand it a bit. Okay. Yeah, I mean, this is I guess a theoretician trying to produce plots. So I guess the point. So what is this line? So this line is sort of how. Okay, so this is one dimension on the logarithmic scale. This is the relative error and the energy density of this model. So everything is continuum. And this dotted line, I guess, is a numerically optimized mirror by Glenn and Gifford. And this black line is kind of what our construction gives, if you choose optimal parameters for a given bond dimension. So we have some parameters which we call K and L, which are not important. So each of these crosses correspond to one data point obtained by our construction. And for a given bond dimension, there's various choices of choosing parameters, and doesn't have to be one. Okay. So you see it's the same trend, but of course our by-hand construction is not just, I mean, it's not competitive. I mean, the exponent is different, right, than the one that you get by numerical optimization. But that's okay. The important thing is that this line stays steep and does not never go off or become flat. Here's another example which is maybe interesting. So this is a Green's function, just a two-point function, ax dagger ay. On the x-axis, it's the separation between x and y, and of course we know that these things should be translation variant in the real theory. So what I'm doing here in these different colors that are so hard to see is I'm actually changing the starting point. So I'm looking, for example, at separation 10, but now these 10 guys I move by one to the right, by one. And so ideally I should get something like this, where it shouldn't matter where I'm moving, where I'm starting, because it's a translation variant system. But for a small bond dimension, this is of course not true, right? You see that there's some problem with translation variance. But then as you increase the bond dimension, and I guess I didn't talk about bond dimension, I said these are qubits. So bond dimension is basically 2 to the, it's sort of mirror language. In our language, the circuit depth is the logarithm of bond dimension. So this is sort of depth 2 or depth 6 circuit in this picture. Well, the thing that is deep is, so these 2 layers will become 6 layers. Which makes it less local in a sense. Okay. So here you see that as you increase the number of layers, then these things really do become approximate translation variant. So that's a feature I wanted to show. So all these, well, the fact that you can distinguish the colors when you look at this picture is what is the translation variance. So in the continuum, we can do something similar, but using a bit more, a few more symbols. So we look at the massless Dirac fermion in 1 plus 1D. And so the vacuum state is filled by this Fermi sea filled by all these negative energy modes of the theory. We'll talk about them more in a second. And then the object that we right now can approximate well is an arbitrary correlation function involving these smeared field operators. So f is a smearing function. Of course, these are they have 2 components, the size, right? There's two fermions. So these are smearing functions. And then you also have things which are basically normal ordered versions of some bilinear operator in the creation of fermion creation and negation operators. So something like a smeared version of a stress energy tensor, or a smeared version of Razor generator. So I'm not telling you exactly how I'm smearing here, but there's a general result for a general bound for whatever smearing you choose, and then yeah, I guess that's the precision I want to state here. So these are the kind of things we want to calculate. So for example, something like multi-point function of, I don't know, say stress energy tensors and whatever you like. And now the result is just as before, that if you compute the exact result, so in the CFT, you get approximately the same result as in the mirror, but now somehow the interpretation of this line is a bit more complicated, because my mirror struct is still a discrete object like before. But these mirroring functions, of course, are continuous functions. So now, what I don't tell you on the slide is kind of how you discretize, or how you reason about these mirroring functions. So what you will have to do is you will have to indeed discretize mirroring functions and then feed them into your network in the right way. And similarly, you have to do something with some of the smearing that you use to define these bilinear operators over here. So there's a sort of a dictionary that's not written here that tells you how to translate this continuum correlation function into a correlation function you can compute in a discrete model. And then once you do this correctly, again, the correlation functions are close and are as close as you wish, as I mentioned before in the lattice theory. Okay. And so this is sort of this hybrid picture where the thing you approximate is continuous, but the thing you're approximating it with is a discrete tensor network, which is kind of funny, but it's also what you would like, for example, when you run this on a quantum computer or somewhere else where you have this gate mindset in mind.
So Michael, so one thing maybe that I missed was, so when you say you're just targeting, let's say 2-point functions or 3-point functions, or you just won't target some n-point functions when n you want to bound it, right?
Right.
So what does that correspond to in the network? Is it the depth, or what controls?
I mean, the way I'll calculate it, I will take a network that looks like the previous one, and I will just multiply these operators at the bottom. Some of what I tell you is the discrete implementation of
right.
of these. Or you mean like how deep does the network have to be as a function of what you want to calculate?
Yeah.
Right. So that's the kind of statement. So I'll give you like a cartoon theorem before, but basically what dictates these properties is it's roughly speaking how many operators you have and how smooth and how locally supported they are. That dictates. So it's a bit like, if you have something that wiggles a lot, then you have to zoom more into the UV, and if you have something that's really wide, then you have to zoom more out because you need a higher IR cutoff in some sense, right? So you need more layers. So there's a precise formula, but it's a bit unwieldy, so I didn't want to display it here yet. Okay, and then once one has this network, one can do, of course, experiment with it, and one can verify somehow what the central charge looks. The way that it looks like. Okay, so here we compute entropies, so that's fine. I guess I should say that because these are free Fermions, and of course the Mertens networks are Gaussian mirror or free Fermion mirror, so all these calculations are very, very simple. We're not really doing a many-body calculation. We're doing everything in a single part of the picture. Now, suppose you ordinarily had a mirror and you wanted to figure out, what is well represented by your mirror, what are the analogs of some quasi-primary fields, what are the scalar dimensions and so on. What you would do is the following. You would try to look for operators that once you push them through one layer of your network, correspond to a multiple of themselves. This multiple would be related to the scaling dimension of this operator, and the operator you would then hope to identify with some primary field or something like this. And so on a technical level, what you do is you kind of take 2 copies of your mirror, this way and its dagger, and you're trying to solve the eigenvector equation, which says, if you plug in an operator O and you apply this in its dagger, you want to get a multiple of O back. So this is an eigenvector equation on the vector space of operators. This is what we call a super operator, which maps operators to operators. And this guy is what you have, what Glenn and Gifford propose to diagonalize to extract information. So in some sense, I'm being a bit disingenuous about this, but in some sense, in our case, of course, there's no need to diagonalize because the theorem tells you just, how, if you want to compute a certain correlation function, what kind of thing you have to compute already. So you kind of don't have to find, for example, what corresponds to the fermion field. You know it a priori. We also, if you want to do a smeared version of stress energy tensor, we also tell you what to do. So you kind of don't have to do this reverse engineering procedure. But of course, if you really want to know exactly what is being faithfully represented in some particular way, then you may still want to do this. But for example, without diagonalizing superoperators, Here's some other plots that you could do. So this is the two-point function of some momentum tensors. I write x and y, but this really is left Gaussian. So it's really smeared. Yeah.
Just a question about your input Hamiltonian.
Yes.
So, like, how do you treat the derivative operator? Is it just like a Haar wavelet picture where it's just nearest neighbor coupling?
Derivative operator in
the input Hamiltonian.
So I mean we are starting with what we know what the vacuum state is here for this construction. So we don't numerically find the network by sort of doing some minimization to find the tensors, but we are sort of constructing it by hand. I'll come back to how we do it in a second, but it's not so we don't have to we never represent the Hamiltonian itself.
Okay.
But for example, I mean but the same question I guess applies to say the stress energy tensor, right, which involves some derivatives. And there sort of we smear things in real space, momentum space, for example, and then the bounds depend on how we smear stuff.
Right, so you can get longer range.
That's right, yeah. And so I guess the only thing that this picture shows you is that, in some sense, you get the right results if the bond dimensions are large enough and so on and so forth. They're not terribly large here. So this is all things that are sort of hidden in this inequality sign, and my saying that there's some mapping between continuum quantities and discrete quantities. And when I say smeared fields, and here I should say non-ordered operators with some smeared kernel. So it's not the exact energy momentum tensor, but some particular smearing of it that we can define. Thanks. Yeah, so I guess, so the only thing I want to say here is indeed, things, two-point functions look the right way. I guess what the parameter here is that changes, again, this is separation between x and y. We are really having little Gaussian packets sitting here, so like small widths, so approximate delta functions. And what's changing is the number of layers in the network. Sort of as the number of layers becomes larger, this picture looks better.
So you're on the line, right?
I'm on the line. Yeah. Where is, sorry, didn't see Michelle. Oh, sorry. Yeah, that's right. Okay, so now, so maybe a bit about how we want to do it, and maybe that's more interesting in some sense. Yeah, so I guess in some sense, so the kind of things that this allows you to answer is, okay, now let's come back to this later. So somehow the point is sort of to being really sure about that you can do things exactly, right, up to some error. Sorry, that you have a rigorous guarantee of what's going on. So for example, let's talk about complexity-related questions later. You can ask me about them later. So how do we produce these things? Well, clearly, since it's a Gaussian state, we want to construct it. We want to solve the problem on a single particle picture. And so the ground state, of course, in either case is just some sort of Fermi Dirac sea filled by negative energy modes of your single particle Hamiltonian, because the Hamiltonian is always the second quantization of some single particle Hamiltonian. And so the question is kind of, can we find a single particle analog of in this case, a mirror tensor network, or this unitary transformation, that allows us to do this whole entanglement normalization business on a single particle level, or this sort of this sort of decomposition of information into position and scale. Okay, so is there a single particle version of a mirror? And the answer is that there is, and that is exactly what a Wavelet transform is. And I mean that's not it's not a new insight. Wavelet transforms have been used. I think even originally maybe there was some contact between the Wavelet community, or maybe Wavelets were invented partly to address questions of renormalization. I think it's maybe not wrong, and then they took off into signal processing. But so here now they're making a reappearance in the context of meritance networks, and this correspondence has been really worked out quite precisely by Glenn and Steve White, where they really showed how to translate this picture. So what is a Wavelet transformation? So Wavelet transformation is sort of a local variant of a Fourier transform. So Fourier transform, right, is something that allows us to decompose a signal into scales in some sense, or into frequencies. But it's very non-local. The basis functions are extremely non-local. So Wavelet transformations are the same thing, but now instead of having a completely delocalized wave, we have a wave packet, that's called a wavelet. And here's something that does not look very wavy, but it looks local. So this is called the Haar wavelet. So here the basis function is just such a kind of a step function, one positive step, one negative step. And now the interesting feature is that as you translate this function and you dilate it, you rescale it, you get a basis of all functions, say, square integral functions on the real line. Okay, so you can decompose any signal into a linear combination of these wavelets as you vary j. J is my scale and their precision. So here's, I guess, an example. So suppose I start with a little bump function like so. Then I can decompose it, for example, in 1/2 times, this particular basis function, plus 1/2 times a wider bump function, which has only half the height. So this is prefactor 1/2 that probably I should have drawn instead of writing it in front. Okay. Now, this guy in turn, you could again decompose in the same fashion because it actually looks the same way as here, just dilated, right? So 1/2 times this guy, we can write as 1/4 times a wider bump function, this guy, plus 1/4 times, well, the step kind of like function, times 1/4 times this even wider sort of, I don't know what to call this, plateau. And so, of course, as you continue this procedure, this guy will become smaller and smaller and smaller, and at the end you can drop it. And so this is an example, right, on a single particle level of a single particle wave function, and I decompose into position scale. And there's lots of choices here for these starting functions, these starting wavelets. And in some sense, the goal of the game is to find ones that correspond to the physics of the system, that have something to do with positive and negative energy modes of our particular system. So that's a wavelet summation. So I guess the notation here is that Wj is the span of all these wavelets at a certain scale. So you fix your scale, so it's scale 0, and you just translate those guys. And then you can change the scale, and you get different spaces of functions. And Vj is the set of signals at scales up to j. So it's like imposing a UV cutoff in some sense. But it's a UV cutoff, but the meaning of what when I say UV cutoff, I really mean I have this particular family of basis functions, and I'm not allowing you to zoom in further on this basis. So it's a set with the sum of these spaces, starting at j. So now, of course, in practice, someone hands you a signal at a certain, well, that has, say, it's maybe bounded in scale. So it's in one of these spaces, Vj, and you want to decompose it exactly in this fashion, right? So someone hands you a green signal, and you want to decompose into these magenta components. This is called the discrete wavelet transformation. So the transformation that does this decomposition for each j, it's such a map, such a transformation, because we have an Osmond basis, it's actually unitary transformation. And it turns out that this is actually implemented by a classical circuit. So classical circuit, I mean, is that these inputs, they correspond to the single particle space. There's no tensor products between the legs. It's really a signal on a line. It's like a wave function on a discrete line here. Or here it would be the continuum. And this circuit, I mean, I'm glossing over some details, but this circuit structurally looks basically exactly like a mirror layer. So what's really going on in practice is you have a signal and you apply certain convolutions with some filters. The length of the filter kind of corresponds to the depth of the classical circuit, and so on and so forth. And the contents of these tensors depend on what you're convolving with. But the point is, some of structurally this looks exactly like a single particle version of a mirror layer. So it's a unitary transformation from here to here. Again, this is imagine this of being, say, L2 of z, sort of the say, wave function on a line. So another, I guess, another way of thinking about what's going on here is sort of you're multiplying some input signals, input signal with a matrix that's sort of a band matrix, right? Because that corresponds to a convolution. But if you think about what this means, how you would actually do such a convolution, you would be led to such a short depth circuit. And so now what you can do is you can just second quantize this thing, and now you get a map from the many-body Hilbert space, Fock space, say, to the Fock space here. And as you second quantize this, well, this becomes exactly a mirror, and it becomes what you would call a Gaussian mirror layer. So unitary transformation, from sort of, well, these n degrees of freedom to these n degrees of freedom, but there's no separation into these sort of a low frequency or sort of coarse degrees of freedom. These are the ones you want to go through, and the fine degrees of freedom corresponding to, sorry, this should be a V. Sorry. So this is sort of signals at scale up to j, signals exactly at scale j, signals at up to scale j plus 1. So this should be a V, excuse me, the same V as here. And so some of this is Vj plus 1, Wj, and all these layers look the same because the whole basis set is self-similar. So all the layers will be the same. So this gives us such a holographic mapping. And now what we have to do is, if we want to construct a particular quantum state, we need to design such a wavelet transformation in such a way that we can target exactly the positive and the negative energy modes. Because then what the network would do is, it would just apply all these unitary transformations, and then it would input some signal here. It would basically create modes here that at the bottom then would correspond to negative energy modes or positive energy modes. So that's what we want to do. So let's coming back to the line. So okay, solving the Dirac equation here, so a single particle Hamiltonian, of course, gets us something like this. So we have left and right movers, and we have a negative energy mode exactly when, say the guys are called chi plus are supported negative momentum, and the guys are called chi minus are supported positive momentum. Sign problems that we won't worry about. Another way of saying the same thing is that the two components in this particular representation that I chose of the Dirac equation are related by what's called the Hilbert transform. So Hilbert transform is something that so you see you pick up a factor of I here from going here to here. But then those guys, they don't get a sign change. Those guys do get a sign change. Those guys are ones supporting positive momentum. Those are ones that are supposed to be negative momentum. And so you have in order to go from one component to the other, you have to implement what's called a Hilbert transform. The Hilbert transform is something that takes a signal, it goes to Fourier space, and it either multiplies by I or by minus I. The positive k components are multiplied by minus I, the negative by I. It's like I guess a 90-degree rotation in Fourier space in one of two directions, depending on whether you have positive or negative momentum. So that's just a repackaging of what's going on between the relation between these two components in order to produce a negative energy mode. Okay. And again, we are stuck because really this is a Fourier transform relation, right? So Fourier transforms are hard. But the point is, of course, that I can choose any basis of my Fermi sea, of my negative energy modes to produce the ground state. So I don't have to work with waves. I don't have to, for example, input into the IK, I into the IK here. I can do any function chi plus, well, any function f and its Hilbert transform here. And these functions, they could be wave packets, they could be anything, except that the only thing I have to manage, I have to guarantee that they're related in Fourier space by in some particular way. So so I guess that's a sort of Nazi here, but sort of the point is to design now a pair of wavelet transformations such that the wavelet functions of the first transformation are related to the waves of the second transformation by exactly this phase relation, by what is called the Hilbert transform. And now it seems like, okay, we changed the problem, but it seems just as hard as before. Happily enough, people solved this problem in the signal processing community. So it turns out that I guess some decades ago there, people, they have been, the Hilbert transform is an important thing in the signal processing community, so they like this. And so they have been exactly looking for pairs of wavelets that satisfy, that are related in such a fashion, because they have sort of nice behaviors. And for example, they really like this property. Somehow they use this transformation exactly to kind of analyze a signal into the analytic and anti-analytic components. So it's a bit like stuff supporting positive K, negative K. So that's somehow a useful thing to also do in signal processing. So they built these objects. And here, here's just some pictures. So orange and blue are now more smooth-looking wavelet functions instead of these hard wavelets from before. And if you look at a certain linear combination corresponding to the Hilbert transform, you see exactly that the negative K components vanish. Well, pretty much, right? So it's pretty good already. But the signal looks like something on the positive component, right? It's like some wave packet-like thing on positive components. So it's not like e to the IK at all, right? So which would be like a delta peak in the Fourier space. But the point is we just get a basis now of functions that are only supported in positive K. And that's what we need. Okay. And so if one second quantizes such a pair of wavelet transformations, and is careful about errors and so on, one obtains now a mirror tensor network for this many-body fermion state. And now maybe we can talk about this picture a bit more, because I told you now that we have a pair of wavelet transformations. So we should have after second quantizing, we should have a pair of quantum circuits. And that's exactly what corresponds to the solid lines in the sort of somewhat darker blue boxes, and the dashed lines in the somewhat lighter blue boxes. So these are two independent wavelet transformations, but they're coupled only here. And so how you should think about this picture is kind of that you're starting with a mode here. That's a superposition, say, of something here and something there. And then you push this through the wavelet transformation. And so what you will get at the bottom is you will get two functions, and they're exactly related by the Hilbert transform. Because the wavelet outputs, the wavelets of one transformation are the Hilbert transform of the other. So so really sort of so what this means is kind of you start with a big Slater joint, a big Fermi sea, where you just fill in some, say a uniform superposition of states here, and then you just apply the second quantized mirror, you get a many-body state that reproduces your ground state, and it would be exactly if you would have exact Hilbert transform pairs and an infinite number of layers. And then to get the wiggly lines, so to get an actual bound, you have to basically worry about these errors. Are there any questions about the rough idea? So the idea is we want to solve things on a single particle level. On the single particle level, it's hard to do Fourier transforms, but what we can actually do is we can actually find pairs of wavelet transformations such that the two modes, sort of the two components of our Dirac fermion, are related in exactly the right way to produce negative energy modes. And of course, now it's clear sort of if you chose an orthogonal input state here, you would instead produce a positive energy mode. And it's probably also clear that maybe the different layers, they correspond to different average energies. So you can sort of control, in some sense, you can build approximations also of excited states. So depending on where you flip the input here. So the whole transformation somehow has physical sense-ish. It's not just a single state that is being prepared, because some of the whole transformation was designed to distinguish between positive and negative energies. Right.
So
yeah.
This is not the regular binary mirror, right? I mean, so the disentanglers and isometries, they're not just 2 to 2 and 2 to 1.
Yeah, so here, yeah, that's right. So here I'm taking this more generous definition of a mirror, which is just a short depth quantum circuit, and then some coarse graining step. You could repackage this into an ordinary mirror, and I think the bond dimension would be related to the number of layers here, if you wanted. So it's like blocking the sides and so on. Thanks. And yeah, the other thing is that this is a fermionic circuit, fermionic Gaussian circuit, so it's not really qubits. So here I really mean a particular single particle state of fermions and so on. But it's understood. I mean, partly by work of Philippe and other people how to contract fermionic tensor networks. All right. So this again, then just to be a bit more precise about what these wiggly lines look like, the approximations look like. So this is the same correlation function from before. And the kind of results so the kind of relevant parameters here are the number of layers that you choose, right? The number of layers in the network. Ideally, you would like to have infinitely many. You want to understand what happens if you truncate, because you have to do some finite calculation. Epsilon is some parameter that measures how well this Hilbert pair relation works. So it's not possible to design wavelet transformations such that one wavelet function is the exact Hilbert transform of the other, but you can do this to arbitrary precision. Epsilon measures this precision. And then there's sort of a parameter that I just call gamma, which is not really doing it justice. It's some constant that measures how smooth are your smearing functions that appear in your correlation function, and how large is their support, and so on. So this dictates in the end, of course, also how deep your network is to be. And so then the total error is kind of composed out of these things. So on the one hand side, your error goes down exponentially with the number of layers that you add, but only up to a certain point, namely up to, and this certain point is dictated by how well this Hilbert pair approximation works. So because the point is, this epsilon tells you how good is your wavelet transformations generating exact negative energy modes. So if this epsilon is larger than 0, you're producing a tiny bit of positive energy always, and so there's no hope of getting to the exact correlation function. So you have to have L sufficiently large, and this epsilon, which is somewhat the design parameter of your wavelets, and we have sort of a procedure by Selesnik that allows us to make epsilon as small as we wish. And right in the third ingredient was this gamma, and so this is some constant I'm being very fuzzy about, but in the 1903.xxxx archive paper, there will be a painfully precise error bound where that tells you how the say smoothness of f and its support enters into this error bound. Right, and as well as of course the number of insertions over here. All right.
So again,
yeah.
When you say that all conformal symmetries are.
Yeah, so I mean this.
You can check this explicitly.
I mean this in the sense, just in the sense that the correlation functions are close. So I'm not talking about say generators or something, and the generators are close in some operator now. So I mean it in the sort of observable way that when you compute correlation functions, you apply some symmetry operation in the exact theory, you know what changes or what doesn't change. And then because of this result, kind of you pick up 2 times the error that's predicted here. So, for example, you know, approximate translation variance and so on. But sort of I guess the thing is kind of, you see, for example, suppose you want to translate things by a tiny little bit, then if f is really smooth, you don't see this, right? So you have to make this f kind of peak to see that you're actually translating. But then, of course, also the network needs to be better, right? And so there's no free lunch somehow. It's just doing the bookkeeping correctly and telling you exactly. Suppose you have a certain correlation function translated by epsilon. How does the error behave?
Could you repeat again? How is it that you get the positive or negative states a momentum?
Like why something like this? It's kind of it's like a design problem. So someone asks you to design wavelets that have this property, and there are various constructors how to do it. I mean, I didn't tell you how we did it. I just asserted to you that people in the signal processing community had done this. I mean, I could explain how it's done. It's kind of like, so they're kind of solving an equation. So you can sort of write this as an equation in some sense. You can say, I want a pair of wavelet functions that are related by the Hilbert transform. This would guarantee this property when I add them, that I only get positive or negative momentum. And then you can try to solve this equation and up to some precision, for example. Or so it's like some minimization problem in the end, right? You're minimizing. Yeah, imagine you fix the size of your circuit, or the width of your filter in the wavelet language, and you're trying to make this as good as possible. That's roughly speaking what you could do. And there's sort of a priori constructions where you don't do a numerical search, but you're really writing down some solution in some sense. But it's, yeah, I don't have a good way of telling you exactly how it's done in this format. But it's clear that if you want to make this better and better, the wavelet must become larger, so things become less local. So I guess you can do it exactly right, and if it's completely non-local, then I mean it relates to also what you guys were doing, right? With sort of the non-local wavelets. Yeah, but then sort of once things are super non-local, it's like an infinite depth circuit in some sense. So if you anyways. It's a bit non-trivial to do these things on a finite level, because the Hilbert transform is not such a nice transformation. Like, things don't decay so well once you Hilbert transform, so it's a bit tricky. All right, so maybe I shouldn't talk about this much. So one can also do this on the circle instead of on the line. In this case, basically by periodizing these wavelets. And so now, if you start with a small wavelet, then nothing happens when you periodize. But if you have something that starts wrapping around, then things become more interesting. What this means on the network level is the lowest levels of networks, they look like as if you had things on the line. But then as you start going up, the top layers get modified, and there's sort of a systematic procedure on the single particle level for doing so. Maybe that's all I should say here. So that also works. I will maybe not talk about Fermi Cs, but you can ask me about it and about branching mirror. So I'll just leave this tantalizing figure on the last slide. So I guess what I was talking about was these mirror tensor networks. So we like them because they're quantum circuits. They have this nice interpretation of renormalizing, tangent renormalization, some kind of renormalization in real space. And I sort of sketched to you how one could get some rigorous guarantees for such a circuit, where sort of the whole transformation has physical meaning based on this wavelet technology. Okay, and then this construction comes with actual error bounds, which is nice to have if one is aiming, for some more general result, and it works in a continuum while being a discrete network. And so I guess there's lots of things to do. For example, the fact that you can somewhat target energies, that makes it interesting whether you can build some sort of double state of some sort, so maybe at least for some range of temperatures, so maybe one can make contact with network structures that have been proposed by people partly in the audience. Other things we don't understand so well. And I guess there's the question whether this toy construction can be a building block for something more interesting, whether one can build more interesting CFTs, or maybe as a starting point for some sort of variation optimization. That would be something else that would be really nice to explore. So I think with this I want to close. Thanks for your attention.
So this explicit construction, how general is this in this rigorous guarantees?
Yeah, I mean it's here it's completely tailored to the baby model, to the 1+1D Dirac fermion. So it's really sort of it's in the same toy model, like solving a problem in like a very detailed problem for simple theory. So it's not. I mean, so the thing that is general is this wavelet mirror correspondence. So so whenever you have a free whenever you want to describe a free fermion state, you could do this possibly, and you could try to attack this by designing appropriate wavelet transformations. So I know, so that's I think a general ingredient, and so I guess what I think this part is maybe, I think this could also be useful more generally. So for example, you want to build some more complicated theory, maybe you take many copies of the free fermion mirror and you do something now on the single particle level to combine things. Or maybe then on the many body level, something non-Gaussian you add on top, but you still start with these as building blocks. So this is something we are thinking about or exploring, but I don't have anything clear to report yet. The wavelet construction itself, they're really targeted to Dirac fermions. But I suppose, I guess the reason, I mean, fermions were not really important, I think, as well. You could just as well do, I think, free bosons, and the only thing that's a bit more complicated is to worry about your local Hilbert space in infinite dimensions. So you also have to truncate the oscillators. But in principle, I think this should also be possible. But the restriction to being free is kind of what makes the whole wavelet machinery work. So if you can decompose your problem into solving a free problem, plus doing something smart on top, that's the motivation of it. Yeah.
It's a similar question. I mean, what came to my mind is that probably you can treat the BCS type of pairing type of approximation for fermions with this method.
Mm-hmm.
The only difference would be that you have to do it self-consistently.
Mm-hmm.
So you decorrelate the higher order things to quadratic Hamiltonian or to problem which is single particle problem. But then you have to self-consistently assure that the correlation functions that you have introduced here Hamiltonian are the ones that you get.
Mm-hmm.
I don't know how difficult it would be, but it seems for me that it should be.
But this is not what Ignacio is doing with them, that they have the double transformation.
I don't know what Ignacio is doing.
Yeah.
He's doing so many things. If I knew what Ignacio is doing, but I think it was yes. Yeah. But I mean, not with wavelets, but they didn't know. No. So in this sense, I'm saying.
But also Andy had this paper on the fast Fourier transform.
I think that's.
Yeah, fast Fourier transform is different, right? Because that's sort of non-local connections. Yeah. So yeah, that's really doing that's of course. I mean, if you only care about counting gates, for example, that's something you can totally do, and you just have non-local connections, like in the fast Fourier transform, and then that's sort of the thing I was saying was hard in some sense, but it's only hard if I want to like a local in space quantum circuit. If I don't worry about locality of my circuit, then that's totally fine. Yeah. Thanks. Yeah. That's very interesting. Maybe we can talk more about this. I would like to learn more about this idea. Yeah.
Just thinking towards the continuum limit, have you looked at all at using continuous wavelets? Like these, where you have a continuous scale parameter? They don't have nice formality relationships, but
no. I mean, I guess not more than that. We have said these words, and we were wondering whether it had something to do. Well, one could give a C-mirror construction along similar lines based on these ideas. That's the extent to which. So I think it's very interesting. Yeah. Thanks.
I think Alex had first, and then.
So on your slide 12, there's some picture of this correlation function. I was just wondering why they're not monotonically decreasing.
So monotonically decreasing.
Conceptual question, like sort of all on the right in particular. Like why did it go to 0 at distance 0?
This is 0 at distance 0. Like this guy?
Yes.
This is 0, right?
Yes.
Yes.
Why does it do that?
Why does it do that? I mean, it's like side dagger, right? I mean, the guy is.
Oh,
yeah.
So it's like a number.
Yeah.
Right.
I think that's okay.
No.
Yeah.
Okay. Sorry, just confusion.
Yes. I used to mention something about
violations of the area law. Sounds kind of a bit surprising. So, what exactly?
In the one-dimensional case, yeah. So I just meant that you know for a gapped model or for massive, if you have some mass gap or something, you would expect that the entropies, they don't scale with a subsystem size, right? Like in a say if you take some gapped 1D lattice model, right? Then some of the area law would say that the entropy is bounded by some constant times the boundary area, which for one-dimensional system is just a constant, right? There's two endpoints. But I mean, in a CFT, entropies, or in a critical theory, entropies are supposed to grow logarithmically with the system size, and that's what I meant by violation. I think, yeah. And there's a similar thing in the right, and yeah. And so like, there's two ways of overcoming this. One is if you use, say, matrix product sets, you just have to use a large bond dimension, right? That's what it's saying, because the bond dimension dictates how much entanglement you can present. And the other way around is you keep your bond dimension, but you have a network that extends in 2 dimensions. And so if you do this cutting, you get a logarithmic divergence. And there's a similar story in the 2-dimensional case, which yeah. Thanks.
Okay, if there are no more questions, let's thank Michael again.